This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Let's try the analysis of this same complex bridge circuit using Thevenin's theorem. If everything I've been saying to you is true, we should ideally obtain the same results for Rx. Bridge network analysis using Thevenin's theorem necessitates we solve for two properties, ETH, the Thevenin equivalent voltage, and RTH, the Thevenin equivalent resistance seen by the load. In this case, our load of interest is bridge resistor Rx between nodes A and B. Let's start by solving for ETH, the Thevenin equivalent voltage. First, we need to remove the load resistor. Then we need to determine the open circuit voltage between A and B. Note the removal of the bridge resistor Rx, the load of interest, has fundamentally changed the nature of this circuit, in that Rm and Rn are perfectly in series with one another, as are Rp and Rq. The series path formed by Rm and Rn is in parallel with the series path formed by Rp and Rq. Nodal voltage A is the voltage across Rn. An application of the voltage divider rule demonstrates that VA is roughly 26 volts. Similarly, nodal voltage B is the voltage across RQ. An application of the voltage divider rule demonstrates that VB is roughly 1.4 volts. VAB is VA minus VB. Substituting our calculated values demonstrates VAB is roughly 24.5 volts. This is the Thevenin's equivalent voltage, ETH. Let's put these figures aside for a moment and solve for the Thevenin's equivalent resistance, RTH. First, we need to remove the load resistor. Then we need to remove the voltage source by replacing it with a short circuit. Finally, we need to determine the resistance at the terminals of interest A and B. This may take some visualization on your part, but the removal of the bridge resistor Rx, the load of interest, and the shorting of the source has fundamentally changed the nature of this circuit. Let us consider the shorted source another node, which I'll call D. Rm and Rn are joined at both node A and node D. Similarly, Rp and Rq are joined at both node B and node D. Rm and Rn between node A and D are perfectly in parallel with one another, a simplification I'm calling R single prime, where R single prime has a value of 175.3 ohms. Similarly, Rp and Rq between nodes B and D are perfectly in parallel with one another, a simplification I'm calling R double prime. The Thevenin's equivalent resistance between nodes A and B is R single prime in series with R double prime. Substituting our given values results in a Thevenin's equivalent resistance of roughly 185 ohms. The Thevenin's equivalent circuit seen by bridge resistor Rx is therefore a 24.5 volt source in series with a 185 ohm resistor. This much simpler pure series circuit can now be used to solve for the electrical properties of Rx, a 270 ohm resistor. An application of the voltage divider rule demonstrates that Vx is roughly 14.6 volts. An application of Ohm's law demonstrates that Rx experiences 53.9 milliamperes of current. These are the same results we obtained earlier using the delta to Y conversion. I have confidence our answers are correct. Take a moment to compare and contrast the two methods. Which method was easier? Bridge circuit analysis using delta to Y conversion or bridge circuit analysis using Thevenin's theorem? The answer is, it depends. Given we had a balanced delta configuration, the equivalent balanced Y was super simple to obtain. This may not be the case for all scenarios. This being said, note we had to do a multi-step series parallel circuit analysis using the delta to Y conversion, and this is only valid for one condition, notably when Rx happens to equal 270 ohms. Any change in Rx would invalidate the entire analysis. The Thevenin's theorem, however, necessitated only two steps, solving for ETH and RTH, and from there it's a simple pure series analysis. This method also yields an equivalent circuit valid for any load element between node A and B. I'm clearly in the Thevenin's theorem camp, however, both methods yield valid results. Alright, that's about it for today. In conclusion, this lecture examined the analysis of complex circuits, circuits in which elements are neither purely in series nor purely in parallel with one another in the form of a bridge network using delta to Y conversions and Thevenin's theorem. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, Be sure to check out the Big Bad Tech channel for additional resources and updates.